we present visual vibration tomography, a method for estimating interior material properties from monocular video. An object's surface motion provides clues to its interior material properties. Given the monocular view shown here of the subtle motion of a bunny, we're able to reconstruct material properties throughout the object. Specifically, we estimate heterogeneous Young's modulus and density values. Even though we only observe one side of the bunny, our method recovers material properties of sides that were unseen in the video, as well as the interior of the object. Our approach is based on a key fact of solid mechanics. Small, linear motion, which we call vibration, can be decomposed into modes occurring at resonant frequencies. In other words, vibration can be expressed as a linear combination of modes of motion. Modes and their resonant frequencies are defined by this generalized eigenvalue equation, which involves the stiffness matrix K and mass matrix M. These matrices are functions of material properties. Given a particular geometry, K and M are determined up to a scaling factor by all the modes and resonant frequencies of the object. However, our input is 2D monocular video. Therefore, we can only observe 3D motion projected onto 2D image space at a limited number of points. Another limitation is that we cannot hope to capture all the modes of an object. Our work proposes a way to deal with this ill-posed problem, recovering the stiffness matrix and mass matrix that best match observed image space modes. We start with an input video of an object vibrating with small motion. Using phase-based motion processing, we extract a displacement field in the horizontal and vertical directions for each frame. We expect image space modes to correspond to peaks in the log power spectrum of motion amplitude. Once we've identified the image space modes in the video, we sample each visible mesh vertex at its corresponding location in the image. These sampled 2D image space modes are the inputs to an optimization procedure that estimates the spatially varying Young's modulus and density values. In this example, it would appear that material properties vary smoothly across the surface of the cube. However, if we inspect the interior of the volume, we can see that there is an impulse change in material properties at the very center. This reconstruction was estimated from 20 image space modes. In one of our experiments, we study a dataset of real videos of drumheads. Here's one example. Note that the human eye cannot tell the exact spatial distribution of material properties based on this video alone. Following our method, we start by extracting the motion fields across time. From the log power spectrum of motion amplitude, we identify image space modes present in the video. This drum has a particularly stiff region in its center, a defect that was introduced by painting gel onto the underside of the drum top. Although the gel is not visible in the video, our method recovers the location and size, as well as relative Young's modulus and density, of the defect. In another proof-of-concept experiment on real data, we tested our method on a Jell-O cube with an interior defect made of clay. From 3 videos, we identified 6 unique image space modes. Note that it is much harder to capture many modes with this 3D object and material. This is due to a high amount of damping, as shown in the rapid decay in the power spectrum, and which we discuss more in the paper. In general, observing more modes results in a more accurate reconstruction. To verify our modal observations, we recreated the real cube in simulation. Here's an animation of its free vibration, based on damping parameters that were estimated from a real video of the cube. The image space modes that we found in real videos roughly agreed with image space modes of the simulation in both appearance and frequency. Even with just 6 constraining modes, we were able to identify an inhomogeneity in the cube with our method. This is further verified by comparing to the reconstruction obtained from simulated data. Importantly, the reconstruction for a cube without a defect, using a comparable set of 6 modes, does not indicate any inhomogeneity. We hope that this result will inspire future work to develop a robust method for real-world objects. Please visit our project page for more details.